As it was already announced, I will take over the part where we talk about how to use pangaeapy, a Python package which was developed and maintained by our team. For this, I would like to ask you a short question of how far you are skilled or familiar with Python. So please just scan the QR code or go to slido.com and answer those questions. So maybe you haven't heard of Python yet, or maybe you're just a skilled R user, or maybe you've actually tried Python once and programmed a small hello world example, or can code a bit, have done a few things, or maybe you're also an expert, or you basically think in Python. Yeah, that looks good. So most of you have some experience with Python. I've been in touch with that. That's great. But don't worry, even if you're a beginner, I wouldn't leave you behind, and you can always ask a question in case something is unclear. It seems like we have quite a few fluent Python coders. That's also good to see. Nice. Yeah, so that's good to know. Thanks for answering the survey. So maybe some few arguments why we should pangaeapy, why should we use a scripting approach to get our data from Pangea in comparison to just downloading them manually. So one benefit is we can do direct data queries in case we are already experienced and Python users who use it every day. So that makes it obviously easy to import your data straight into your script and then work with those data. That's quite a handy thing to do. It's also easier to bulk download your data instead of just going to the websites to each single data set and downloading the data table, which can be tedious if you have, I guess, more than 20 data sets already. Another advantage is you can more easily search for metadata from within Python and analyze that in case you're not purely interested in the data, but more on the metadata. And one good thing is also you can have an automated workflow for your data mining approaches and also repeat that in case you want to see if there are updates coming in for a certain search term, and there are more data sets coming in, so I can repeat or rerun your script and get updated results from your search. And probably one of the most important arguments is that your workflow is reproducible. So having a script approach, either in Python or R, doesn't matter, you can really reproducibly show how you have done your search, and especially if you do a big metadata analysis, you can really transparently show how you searched and downloaded your data. And then ideally, you can also attach that to your manuscript later on. So as I said already, Pangea has been developed and maintained by Pangea staff. So the good thing about this is we have basically paid staff sitting behind there who keeps checking that everything is correct, and if there are any bugs and errors, that they are fixed relatively fast. It's open source, so we have all the source code on a GitHub account, which also means anyone can contribute. So it's a public repository. So if you have any good ideas, some nice code snippets you want to contribute and a thing that could be useful for pangaeapy, just fork the repository and suggest those changes. At the same time, if you find any bugs, you can also report these issues in GitHub so we can see them and can fix them as soon as possible. So in terms of getting started, getting it running, if you have already Python installed, it's quite straightforward. So you just go to your Python environment on your local machine and just enter pip install pangaeapy in your terminal. So it's basically listed on pip, and they can simply install it pangaeapy. If you want to import pangaeapy after you installed it, you can just enter import pangaeapy as pan, for instance, or you can also access specific methods via the from command, where you can, for instance, import the PANGAEA or the PANDataset method individually. And then, as Flavia already mentioned, so there are basically two very essential commands. So there are many commands, but these two commands are basically the ones you should keep in mind. So one is the pangaeapy command, which is basically just mirroring the same thing as when you would go to the web and enter a search term into the search bar on the website. And here, for instance, you would enter your search term. You just have to use quotation marks, and then you would get a result list with a different data set DOIs and with a score, like you also saw that with Uwe's presentation. What is done is basically it's doing an elastic search, which searches for all the different text elements of PANGAEA to find that search term, and the best or the data set with the best score is listed on the top, and then obviously the score goes down further down the list. The other most important function, one very important function, is the PANDataset command, where you can directly download a dataset. So you can, for instance, just enter the DOI in this command, and then you get the data table attached to this dataset publication downloaded, and it would look like this. Yeah. So for our practice today, so it's not going to be just a lecture. So we have a lot of practice elements today. We will work in a Jupyter notebook via Colab. We mentioned yesterday, if you do not have a Google account, you may also be able to use the notebook by downloading it on your local machine and start it from your local Python environment. If you do have a Google account, you can access the notebook right in your browser. I'll show you in a second how it's going to be done. Just for now, an explanation. So you would basically go to the GitHub account or our PANGAEA Community Workshop GitHub account, and there you would find the notebook. There you can navigate to the Python folder, where you find another subfolder called Get PANGAEA Data, and then there you would find a Google Colab badge in the README, where you can click on it to start the notebook. I will show you this in a second. Just in case you haven't seen a Jupyter notebook yet, so in Colab it looks like that, where you have a main window. You have, for instance, a table of contents on the left side, where you can click through the different contents of your notebook. Then you have the main notebook itself, where you have some text which explains what's inside the notebook, and then you have gray shaded cells where you can execute the actual Python code. Yeah, and for that, we can start with the Jupyter practice. So I will go to my browser, which I have to close down here. One moment, I share that again. So you can see my browser, hopefully. Yeah, great. I just have to click these Zoom windows a bit around. So you would go, I hope you all have your browser opened. So you would go to GitHub. And then in the search box for GitHub, you enter PANGAEA Community Workshop. And then you would find one repository. And that's the repository where you can click on. And then you go to Python. So you can see all the different folders which we have here. You can also see our R folder, which Flavia mentioned. So there you can also click on, and you find, for instance, all the different R examples, but that's not the topic for this session. So we would go to the Python folder, and there you can find the subfolder Get PANGAEA Data. And there you can see two notebooks. So you can see a Get PANGAEA Data and a Get PANGAEA Data Solutions. So the solution notebook is for me, and the one above is for you. So I would ask you to go down, or do not click on the the notebooks directly, just go down and they can see a Google Colab link on the badge, and you can just click on that. And once you do that, you get your notebook open. Yeah. Do not click on a solutions notebook yet. That's only what I'm going to do, or you may want to do later on after this workshop today. And I will just post a link right now to the GitHub page in case you have not been able to follow. And then we would be on this page. So just turn on you. So maybe you can just have like a thumbs up or some kind of sign that you've worked it out to access the Jupyter Notebook. In case you get completely stuck, just let me know. Did you all find the link in the chat? So in case anyone has trouble to do that, also no problem. You can also just follow me because I do a live demonstration. That's also not a problem. So I just minimize it again. So again, we have here the table of contents where you can click through the different menus if you want, just for a quick navigation. But we want to start from the top. And here you basically have different elements. So in case you haven't used Jupyter Notebook yet, you have like text elements. So you can click in that, for instance, and see the raw code, which is Markdown. And you have code cells like that, where you can execute your Python code. You can enter new code fields when you just, for instance, hover just to the edge of a cell. You can, for instance, click on code, and then you can add a new code cell and do anything here for code. You can delete that again with this trash bin, or you can enter a text field where you just enter some text here just to document what you have done. So it's a really nice way also if you want to present your analysis for a paper, really nice way to document your code at the same time. Yeah, so the first thing we do is we import all our libraries. So that's quite a bit. For that, you see that if you, for instance, go down or hover over the field, you can see a play button. So you click on the play button. And you see a bit of a warning because it's not Colab code. It's from next to a GitHub account, but we know it's safe. So you just say, OK, I'm fine with that. And then we execute the code. Then you can see a little snake running around here, which just shows that it's executing the code. And you see like the green triangle that shows you what it's doing right now, where it is. You notice that we had to do some manual installing. So Google Colab has quite a lot of packages already installed. However, not PANGAEapy and apparently not BioPython. Yeah, if you don't, you only need to do this once. So in case you want to re-execute your notebook, you can also hashtag that out so it wouldn't execute the pip install again. And then we're good to go. So hopefully you all got a tick mark here for importing the libraries. Just checking anyone has an issue with that. And then we can do our first exercises. So simply querying. So you already saw in my presentation that we want to can do a simple query with this search term, which just mirrors the search on the website, with the PANGAEA website. So we use the pangaeapy command, enter any search term you want. In this case, you want to look for data which dealt with wheat. And then we can save that. So we can save the query in a query variable. And then we can retrieve different information from that. So it is executed for now. And then we get a result. So what happens? So we can, for instance, when we check the query command, we press dot, we can get different attributes from that. So we get, for instance, the total count, which tells us how many results we got from that. So how many search results we got from the search. But the more important one would be the result attribute, which would give us, not results, result. All this different information, which look a bit cryptic, but you get basically the DOI for a search result, the score, and other information. And to make this look a bit nicer, I converted this whole thing to a pandas data frame, so it looks more like a data table we know from R. And then save that, and then just show the 4 top entries of our results. Yeah. And there we can see the UI for the data set that get the highest score. So it's done with an Elasticsearch algorithm, and the data set with the best score are listed the highest. And then we also get HTML content, which can be a bit cryptic, but that you also get with this result. Something that I need to explain is the type section. So we have different data types. I think it was mentioned yesterday. We have like data collections. Here in Python, it's called parent. So this is actually a data collection, and a child would be an actual data set. So parents wouldn't contain data, but the data sets, like the child data set, they would contain the actual data. Yeah, so it's important to know. And then we can also do more complex queries. So very similar to what Katrin explained yesterday. So we can combine different search terms. If you just chain them together, we basically can spare the end. So it would automatically recognize it as marine and geology. And then we click on that. And then I have a little print statement here, which shows us how many search results we got for this query. If you go a bit more advanced, for instance, if you want to look for a species which has, or if you want to look for 2 different species with the same genus, you can, for instance, enter the genus, and then in brackets you can add the alternative species names separated by an OR function, and it would look for these 2 species basically. And you execute it again, and then you get those search results. The same thing if you're not sure about how a certain species or genus name is spelled, you can again use that question mark to indicate that this can be any letter in this particular position. And you execute that and get those search results. Another one is the tilde sign, which you can add before a search term in case you're uncertain about the general spelling of this term. So it's getting really generic. If you add this tilde, and then you get search results for all these different, for this particular search term. And we also learned yesterday, if, for instance, you would just look for an author called Hertschuh, then without the prefix, then you would basically also not just look for data sets where the author is in the title or in the direct citation of the data set, but you would also look in the references attached to the data set and anywhere where that name would be mentioned. But if you want to be specific and you only want to get an author from this data set, then you would need to add, okay, only look in the citation and look for the authors in that citation. And then it would be very specific. And again, you have to pay attention that you don't have any spaces after the colon. Otherwise, it wouldn't work. Yes, and then we also heard some actually looking for data sets by using a bounding box. So we had that web interface yesterday where we could enter the different geolocations. In PANGAEapy, we have the bbbox attribute where you enter the latitude and longitude as a rectangle here. And for instance, then you can enter a search term and constrain that search term. Okay, find data sets that have that work with that species or contain that species term, but only within that geolocation. Yeah. So that would basically this what we have done and learned yesterday via PANGAEapy. So that's very straightforward. It doesn't take much code. Again, if you need to look up the keywords, you can go to our website and find all the different ways how you can specify certain field names and see to and check how you can make your search more specific. And also in terms of all the different variations, how you can enter search terms. Also here the tilde. So then you may have noticed already we have a limit attribute here. So what does it mean? So we may get a lot of search results via Elasticsearch, But often, if you have, let's say, 5,000 search results, the record 4,999 may not be that relevant anymore. It may have a really low score, and that's the reason why we limit the search, because we assume that also the 500 listed terms are the most relevant ones. But there may be cases, for instance, if you have really specific searches, for instance, with the author, where you know, okay, if that author is in that citation, I really want all the data sets. You may want to overcome that limit. So it's not that straightforward. What you have to do basically is you have to package your search. So you have to not only increase the limit, but you also have to have an offset in there where you basically start downloading the data from the next 500, so from 500 to 1,000. So I need an offset as well. And for instance, if you want to download the data sets from 1,000 to 1,500, you need to have an offset of 1,000 and a limit of 500. It's a bit complicated. That's why I packaged this in a small function, which you can just execute. So we save that function. And here you see, okay, if you have a limit for more than 500, then we change the offset and to be able to download the results beyond 500. Another addition to this function is that we also only want to select the child, also the actual data sets, not the data collections. So we're interested in the data itself. And we may be not that interested in the HTML code and the position of the data set, which was in the results data table. So we just drop that. And at the same time, we add the query term, which we used, into our results table. So that's executed. And once we apply this, or we look for the author Herzschuh, then we say, okay, we had more than 424 data sets. And we have again the search results without the HTML column and our query term included, and only the data sets itself without the data collections. So then we have just a small helper function, which is not essential. It's just useful in case you want to save data sets, so we can enable it easier. So we just extract the particular PANGAEA ID here, not the whole DOI. So that's just really just a small helper function. And then we have the ID here added to the data table. And maybe now a short quiz. I just have to hide my solutions. So I think I'll just share this. See if I can see you. So I would like to know, if you perform a search, how many data sets contain the species Octopus vulgaris? So you can type in your solution here and execute that. So you can just copy paste the code from the top, from the queries section, and you can just shout out in the shout out when you found the result. So then the next question would be, how many data sets contain the Gardus moroa, so the Baltic Sea cod, in the title only? So remember, you have to specify the keyword before the search term. You only want to look in the title. And did someone find out?
I'm getting 54.
54? Let's see. Yes, almost. I guess that's the same. Astrid, did we do the exact same thing?
No,
Sorry, the problem on your query is your solution is not 100% correct, because you're only searching for Gardus in the citation, but Mohua can be anywhere.
Okay. Yeah, then
you need to put quotes. You need to put quotes around the Gardus Mohua, I assume. Yeah, the problem is you need to escape the quotes.
Yeah, so that's one thing. Yeah, we have to check that we do not also change that.
Two types of quotes, and one is used already for the full string, and then you need to use the other one to like constrain the string results.
Exactly. That doesn't make any difference. We just have to make sure we don't repeat the same quotes.
Yeah.
So we just have to alternate them.
Otherwise, it would be it would be two strings.
Yeah, the other workaround would have been to write citation dot colon title before each word.
Let's move on to the next question. So let's try another thing. We want to look for data sets that were only published by Hannes Grobe. Did someone find out?
I'm getting 3,249.
Yeah, me too. I have the same.
Yes, that looks good. So we just add author to the citation because you just want to look in the citation, and then for the author, and just enter Grobe Hannes, and then we get that result. Very good. And the last one will be a bit more tricky. How many data sets were measured with the parameter temperature water using a CTD reset? So it's a bit more advanced. So remember, we have the parameter we can specify, and we also have the method term. Try it out. Yes, a very productive author. A very productive result, sorry, not author. But we may have some authors who actually get close to that. Yes, the code would be that. So you specify with the parameter that you want to use look for water temperature. And then in the method, you can specify only give me the results that you use the CTD reset to measure this temperature. Yep, great. I still get
but this only works in that case because it's very unlikely, or in most cases, it doesn't matter if water can appear anywhere, but actually the query is wrong, but returns the same results. So, but in most cases, you don't really need that detailed information, because if you have some additional data sets in your query results, who cares? They will also be at the end of the list of results. In most cases, they are not so relevant. It would theoretically would be enough to simply enter temperature, water, CTD, and rosette as 4 terms into your query, and I think the first result return will be exactly the same. Only the total number might not be exact.
Yeah. So it also shows you also need to verify the single data sets as well, that they contain the data you want. That's obviously the next step as well. So the next section would be how to actually download data sets. So of course, that's the most relevant part. We want to get the data. And for this, we of course first have to perform a search query and save the results. And what we are after is basically the DUI of our dataset from our search query. And what we do basically is we take that DUI. It can be written in different formats. In this case, it's this format and not this way. And then we can use the PANGAEapy command to directly download our data. And then it's going to look like this. And it's basically saved in an object, so you can see if you just enter ds, so we saved it in ds, and then enter dot, you can see that there are different information saved. So it saves them different metadata, for instance, such as abstracts and so on, authors and so on, but also the actual data. So in order to access the data, we need to enter dot data in order to access those data. And that's the data table. Here you go. Yeah, and the nice part is the search term here can be quite flexible. So we can either enter the full DUI, which would be the DUI if we click on it, which go to the landing page of our data set. Yeah, so we can enter the full DUI, but we can also just enter the DUI, which we got from the search results here. It is not a direct backlink, so we can enter that as well, get the same thing. And then we can also just enter the ID. and we get to this exact same result. So there's some flexibility if you want to access a certain data set. One shortcoming is that we get abbreviated parameters. So like the names for our variables, they are abbreviated, and we also lack the unit. So what we can do is there's a small helper function for that, where we get the long parameters and the unit as well. So basically I look within the parameter values content of what we saved and then extract the unit and the parameter, the full parameter name in that. And in comparison, like this was the old version, yeah. And here in the new version, we have the original long parameters. So for instance, here depth water includes also the meter unit, yeah. And everything is spelled out. And then maybe you want to have a short look of how our data are distributed in case it's this, for instance, I think an abundance data set. So we can have a look, plot a map, and then see where all the data points lie. And plotly, we can of course nicely label that. We can see the different parameters attached to each sampling point. So it's a nice thing we can do in Python to get an overview of what we have actually downloaded. And then of course you want to download that. Right now it's just in our Python environment. So we want to download that to our local machine with this code. So we basically here, I just create a data folder, which I termed PANGAEA data, for instance, and it creates the folder. And then I will save the data with as a comma separated file in that data folder. So I execute that. And then in Google Colab, you have that folder sign, which is showing you all the files which you downloaded locally, not on your machine, but actually in Google Colab. So that wouldn't stay. So once you close Google Colab, these data would not be there anymore. So that's the only disadvantage of Google Colab. But if you run Python then from your local machine or in a GitHub, in a cloud environment, maybe with using Jupyter Notebook, you can download it to the cloud as well. So here, for instance, you can click on that, we download other data as well, but you would find that data set here. That's the data set we downloaded. So I can actually just delete that shortly. Okay, it doesn't do that. Yeah, but it gets downloaded here, and that's all it does. And here we get a next function where we can download multiple data sets. So here actually we have the strength of scripting, accessing our data via scripts, because we can save a lot of manual clicking work, which we would need to do via the website. So we perform a search query again. And then we basically loop over the different IDs or the different DOIs of our search results. So like all these things which are listed here. And download them in a loop. So we click on that. And then would basically, it's work in progress. So it's the first data set I got downloaded. Now it's working on the second data set. And then here's the third one. Oh, it was the fourth one already. Yeah. So I just limited that to 4 data sets. Of course, you don't want to do this for 500 data sets. It may take a while and put a bit of stress on our server. So if you just want to try, just keep it to a low amount. And yeah, and then you have it saved. I already saved them beforehand because I test run the script, and it would pop up in your folder once you press the save button. So again, what it does here, it's not directly saving it straight away. It's just saving it in a dictionary. So it's a Python-specific data format. So it's a dictionary and saves all the data sets in there. And then you loop over the dictionary and save it, save each separate file as CSV, and label that also with our PANGAEA ID. So that's also why we extracted the PANGAEA ID beforehand. So it makes the labeling easier for your files. Yeah, so maybe again, some short quiz. I would like to ask you to download this data set. So all you would need to do in this case, use the PANGAEA, the pan data command, and paste that link in there. And then tell me what the name is of the first event. So there's going to be an event column. And I would like to tell me what the name of that event is. Exactly. Well done. The next part would be, that needs a bit of Python coding. I'm not sure if you want to do this. Yeah, let's do that. Maybe skip the last one. So download this data set and tell me how many sampling points we have above 1,000 meters. So there's going to be an elevation parameter in there. And you will need to filter all the data points which are larger than 1,000 meters. So it's probably more for the intermediate Python users. And here again, it's a nice part of using the script because we can loop over different data and basically check, okay, which data contain elevation, and then say, okay, we're only interested in anything above 1,000 meters. Something we can also easily do with a manual approach. 24, that's correct. Well done. So we download the data set here, and then we have a filter command where we filter everything above 1,000 meters, and then we get 24 sampling points. Great. As last task, which I'm just going to lift right now because we're also running short of time. So that's, for instance, where you want to see, okay, are there sampling points for this data set in Australia? So we download the data set and plot it on Plotly. And then we can see that these are mainly, that there's not a single point in Australia, but we have data points in Russia and Siberia mainly. Okay, and now we go to the more advanced section. If you do not manage everything because you may run out of time, it's not too bad because it's also all documented in the notebook, but I will just walk you through it as far as we can. And as I mentioned earlier, one good thing we can do is we can look for metadata. So if you want to do metadata analysis for data sets, we can do that quite easily, nicely via Python. So as I said, when we download a data set, it gets all the information gets saved in an object, which we just labeled DS here. And then, I don't know what you're showing now. Yeah. And then we can extract different metadata. So for instance, we enter DS title, we get the title of the data set. If you want the abstract, we can just need to enter .abstract. If you want to get a publication date, it's date, and so on. So there's a lot of metadata we can query. Some are maybe not that straightforward. For instance, if you just enter DS authors, we just get another object returned. So because there are multiple authors. So we basically need to unpack that to access all these different authors. And that's done with this list comprehension here. The same thing for the ORCIDs. We also need to unpack that. That's also hidden in a DS authors object. Then the citation on the other hand is again quite easy to get with the citation command, the DOI as well. And also, for instance, the coverage, which is basically the mean latitude or the mean longitude for this data set. In case you have multiple sampling events, as we saw on the map, then it just displays the mean geolocation for that. Also, maybe the parameters in units. We already had a function for that earlier. And also the events we can also extract as a data frame as well. And once you do that, we get basically a nice output. We can see here the title of the project, the abstract, publication date, then the different authors, citation and the authors, ORCIDs, and so on. So lots of metadata which you can use for whatever we want. Also maybe important to see what parameters are actually included in this data set. Then we go to the next level and would basically extract metadata from multiple data sets. And for this, I basically wrap this whole thing up in a function which saves all the metadata in a pandas data table. Yeah, so basically repeats the same thing, such as querying the year and the authors, but packs everything in a nice data table. And then it uses that to do this over multiple data sets. which includes also creating a folder where it basically then also saves that metadata table into a CSV file, so in a comma-separated file. So once we execute our thing, so for instance, looking for, again, for the author Herzschuh, then we get a nice list starting with the PANGAEA ID, then, for instance, when it was published, so let's go to the top, the authors, the title, and all listed nicely in a full data table. And you can obviously just also select what you, if you don't want every single content, you can also reduce the data table to a smaller size. Yeah. So that's how you can extract metadata. There are also more advanced ways of doing that, such as scraping the HTML. I will not go into detail for this now. But it's pretty much very similar to what Uwe mentioned in terms of doing a curl request. You can download the HTML content of the PANGAEA dataset, or you can also do this also for JSON content. So that's all possible here. But I think that goes in a bit too much in detail. But if you're interested in that, you can also have a closer look at home and walk through the code. But just to show you that it also got saved here. So we basically have a folder here, it's called PANGAEA Metadata, and there you can see the metadata file for your particular search, which gets also labeled with your search term, for in this case, for instance, citation author and Herzschuh. Yeah, maybe one short quiz again. So what is the title of this data set? So try that out. So you paste the link in for your search and then just try that out.
In situ metabolic rates of the coral Platygyra canosa in Port Island, Hong Kong.
Yes, exactly. So that was the code for that. So we save everything in DS and then access the title with this command. So the next task is just very, very similar, just a different attribute you want to query. So what would be the publication date of this data set? Check. Yes, that was correct. And code for this would be this. So you can query this with ds.date. The next one I'm just gonna demonstrate it because we're running short of time. So that would be, for instance, okay, we just want to look for the parameters and we're just interested in, okay, I'm looking for if this data set contains temperature. Yeah, then we would basically, first of all, convert the parameters into long parameters. Yeah. And then we would query the columns of the data set if they contain temperature. And the way it looks like would be this. Because there we have, for instance, the issue that we get multiple hits for that. So we get, for instance, temperature itself, what we want, but we also get something like, okay, there was another parameter which contained temperature, but it's not what we're actually looking for. So we can also specify that by just saying, okay, just look for parameters that contain the unit degrees Celsius. And that's what we get then. And we have the parameter. So yes, we have what we want. Yeah, so there's more content, which is more advanced. So the next thing is how we can actually, that gets quite interesting now, because now it's about performing something where we extract parameters that are spread over across different data sets. And let's say we are only interested in one or few parameters and we don't want to extract all the data sets completely, but just, for instance, just temperature or just pressure or just depth. And that's what we can do with this. It's basically mirrors what we can do also via the data warehouse in PANGAEA on the PANGAEA website. And the way it works is that we basically can combine, like first of all, we do a search, and then we can combine the different parameters from a search across the different data tables, retrieve them, and then search all the headers for the different data tables and combine them in a single data frame. And what we get is basically a list of different parameters. Yeah, so it's just a snapshot of the first 10. So if you have a closer look, we can, sorry. If you want to see more, you can also do this. And we can see more parameters. So these are all the parameters pooled across all the data tables you downloaded in our search. And then, for instance, we can just plot that and see, okay, which parameters have been there very often. So like, for instance, this we had occurred 7 times in data sets. And we maybe have, I don't know, depth we have like in 3 data sets. So we can get a bit of an idea what parameters we have in our full pool of data sets we search for. And then I have a function here, pre-program, which would basically extract those specific parameters which you're interested in. Yeah, let's say you want to only want to have the latitude, the longitude, the date and time, and the depth and salinity across all these different data sets. Yeah, then you would basically just execute that function, and it would combine that in a single data table and put that in your data folder. So here, extracted data in the CSV file. And you also notice like some data sets, they actually did not contain depth, but they contain the other ones. So it just pools them and you have everything combined. So that's quite a handy function to have if you want to extract parameters across different data tables. Then sometimes you also want to combine data. So we also may get heterogeneous data. So data that are tabular, which are stored in Pangea, but they will link maybe to genetic data. So we have combined submissions sometimes where we get genetic data and environmental data. Pangea does not store genetic data, as Janine mentioned yesterday, but we can link those data because often we have data sets that say, okay, you can find data at NCBI, for instance, which are linked to this Pangea data set. Then you can, for instance, this is an example here. We can download a data set which contains genetic data. So you can see an accession number for genetics. So we do not publish the gene sequence itself, but we get, for instance, an accession number to a genetic database. Yeah, and then we can query that to combine it with our data set. And for that, we use, for instance, here we use the package to retrieve NCBI data. And we basically then use these accession numbers from the data table to download the sequences attached to that. So it's getting the data from NCBI. You can see here, it's looping over the different accession numbers, which you could basically see here. Yeah, these are the accession numbers. And once you've done that, we can attach it to our data table. And you go to the end of it, you can see here, we got another column, as well as the gene name, and we got a sequence for this data set, which is related to our environmental data stored in Pangea. Yeah, and last but not least, we have one function of, for instance, we sometimes also binary files, so it can be image data, which are stored on Pangea. So for instance, we go here, we click on that data set, we can see here, was it this one? Probably not. Let's go here first again. I think it was the wrong link, whatever. So we can have a data set with image data. Yeah, here it is, where you can see a JPEG attached to a data set. And how do we get those image files downloaded? So one way is to do this, where we basically create a URL, an image URL, which is then pasted into a link to access those files. So what basically do, we take this image description and paste it into this link here, maybe this image, and loop over it, loop all over these image file names, and then download them. And then you would see, hopefully in a second, that these images pop up here. And it also creates a link. So for instance, if you click on a single link, you would see the image opening up here. Yeah, so that can be very handy if you have video files, image files, and lots of them, by more easily download those data on your machine. Yeah, so that's it from my side. Hopefully I didn't lose too many on the last part, but as I said, the Jupyter Notebook is available in our GitHub account. Have a look. If you have questions about it as well, you can always ask me too. Not a problem. We can maybe walk through some things as well, if you like.